Okay, let's start with a kind of a wild thought. What if the universe is a symphony? Not of sound, but of something way more fundamental.
And what if everything in it, I mean every particle, every force, every single star, is just a different note being played by a tiny vibrating string? That right there is the radical, the elegant, and, yeah, the deeply controversial idea at the very heart of string theory. It's our best candidate for a theory of everything, a single idea that could finally bring peace to the warring laws of physics.
So here's what we're going to dive into. First, the big problem string theory is trying to solve. Then, its beautiful symphony of string solution. After that, the mind-bending idea of hidden dimensions, how the theory ended up unifying itself, and finally, why it's still very much a theory on trial.
All right, let's start with a universe at odds. Because to really get why we even need a theory as strange as this one, we first have to talk about the biggest, most frustrating problem in all of modern physics. For the better part of a century, our whole view of the universe has been split right down the middle. We have two incredibly successful theories. On one side, there's Einstein's general relativity, which describes the universe on the grandest of scales. And on the other, there's quantum mechanics, which describes it on the tiniest scales. The problem? They absolutely hate each other. Think of it this way. General relativity is the king of the big stuff. Planets, stars, the cosmic dance of galaxies. Quantum mechanics, well, it's the undisputed ruler of the small stuff. Atoms, particles, all that quantum weirdness. But here's the real kicker. They're written in completely different mathematical languages. And when you try to use them together in the most extreme places you can imagine, like inside a black hole or at the moment of the Big Bang, the math just breaks. It spits out nonsense. Physics needs a translator, a new theory of quantum gravity to finally bridge this great divide. And that is where the symphony of strings comes into play. Back in the 1970s, this radical new idea started to take shape, and funny enough, it didn't start as a theory of gravity at all. The core idea is simple but profound. What if we replace all those point-like particles with tiny one-dimensional objects called strings? So instead of thinking of an electron as a microscopic dot, imagine it's a tiny, vibrating loop of energy. And all its properties, its mass, its charge, everything we can measure, are just a direct result of how that little string happens to be vibrating. And this is where the real power of the theory just shines. It's like a cosmic guitar string. If it vibrates one way, what we see is an electron. Vibrated another way, and what we see is a photon, a particle of light. And here's the absolute game changer. A third vibration pattern gives you the graviton, the particle that carries the force of gravity itself. Just like that, all of matter and all the forces become unified. They're just different notes being played on the same fundamental string. But, of course, an idea this beautiful has to have a catch, right? Oh, it does. And it leads us to some seriously mind-bending consequences. Welcome to the hidden dimensions of reality. You see, for the math of string theory to actually work, the universe can't just have the three dimensions of space we see plus time. The best way to wrap your head around this is the old garden hose analogy. From way across the lawn, a hose just looks like a one-dimensional line. But if you were a tiny ant crawling on its surface, you'd know there's a whole other dimension, its circumference, the part that goes around. String theory suggests that there could be extra spatial dimensions all around us, just curled up or compactified into a space so tiny we could never ever notice them. So how many dimensions are we talking about here? Well, for the leading versions of the theory, what we call superstring theories, space-time must have 10 dimensions. That's 9 of space and 1 of time. And let me be clear, this isn't some random guess. It's a strict mathematical requirement. Without it, the whole theory just completely falls apart. Now, this quest for unification didn't just stop with particles and forces. It turned out the theory itself needed to be unified. So by the mid-1980s, things got a little messy. Physicists had found not one, but 5 different consistent versions of string theory, which isn't great for a supposed theory of everything. But then, in 1995, a physicist named Edward Witten came along and proposed this absolutely breathtaking idea. What if all 5 of these 10-dimensional theories were really just different ways of looking at a single, much deeper theory, one that lives in 11 dimensions? He called this mysterious parent theory M-theory. And this is that grand unification. It turns out all 5 of those seemingly separate superstring theories are connected by these profound mathematical tricks called dualities. Think of a duality like this.
You're looking at a sculpture from two different angles. They might look totally different, but they're describing the exact same thing. These dualities showed that all 5 theories were basically just different translations of the same book, all pointing back to one underlying story, M theory.
And yet, for all of its mathematical beauty, for all of its promise, string theory is in deep trouble. So for our final section, let's look at why it's still very much a theory on trial. This number right here is maybe the theory's biggest hurdle. Remember those extra dimensions and how they have to be curled up? Well, when you try to calculate all the possible ways they could be curled up, you don't get one nice, clean answer. You get a number of possibilities so huge it's hard to even comprehend, an estimated 10 to the power of 500. Each one of those describes a different possible universe with different physical laws. This is what's known as the string theory landscape. And this landscape problem is a potential killer for the theory's predictability. I mean, if your theory allows for almost any outcome, how can you ever really test it? Beyond that, there is a complete and total lack of experimental evidence. The energies you need to actually see one of these strings are trillions of times greater than anything our most powerful particle accelerators can dream of reaching. And then there are critics who argue it's not even a fundamental theory, because it has to assume a pre-existing stage of spacetime for the strings to vibrate on, instead of explaining where spacetime itself comes from. This quote from physicist and vocal critic Peter White really just hits the nail on the head. With so many possible answers on the table, the theory runs the risk of being so flexible that it doesn't really explain anything at all. It loses its predictive power, and that's supposed to be the hallmark of any good scientific theory. And that leaves us right here with the ultimate question. Is string theory's hidden symphony the true music of our cosmos? A theory of everything that we just haven't figured out how to prove yet? Or is its vast landscape of possibilities a sign that it's just a beautiful piece of mathematics, a theory so flexible it's capable of describing anything, and therefore a theory of nothing? Right now, the jury is still out.